Okay, today's video lesson is going to be on Lewis structures and formal charges. Okay, a lot of times when you're drawing Lewis structures, if we look at something like carbon dioxide, most people should know to draw the carbon dioxide like this, where you got the double bonds on either side of the carbon. But what's to say that you can't draw it with a triple bond on one side and a single bond on the other? Okay, so if we follow our rules for Lewis structures, you could end up with two versions of CO2. Okay, so you should know this is the right one, but we're going to use what's called formal charges to explain why that happens. Now, before we do that though, let's just talk quickly about what a formal charge is. If we think about ionic compounds like sodium chloride or lithium sulfide, we know that they're made up of ions. So we got a sodium ion and we've got a chloride ion, right? Or we've got a lithium ion and a sulfide ion. Well, these are actual true charges that are given to those elements because of the fact that we have an electron transfer from one element to another. Okay, so that's the first type of charge that we've talked about, is something called a real true charge due to the transfer of electron. Well, with molecules, the electrons aren't necessarily being transferred between the two, they're just being shared. So there's no complete charge that's going to be formed between these two ions, but they are sharing the electrons unequally. So when we deal with molecules, we're going to actually look at two different types of charge. We're going to look at something called an oxidation state, or an oxidation charge, and a formal charge. Oxidation charges I'll actually talk more about in a later video, but in this one we're going to talk about what are called formal charges. So to deal with that, we have to know how to deal with these bonding pairs of electrons. Okay, so when we deal with formal charges, what we're going to do is we're going to ignore electronegativity. Okay, when we do oxidation states or oxidation charges, what we would do is we would actually magnify the electronegativity. Okay, so it would be the opposite of what we do for for formal charges. So electronegativity. Okay. So what we're going to do, this is going to ignore electronegativity. So what that means is if we look at the bond in our oxygen and our carbon, they're sharing electrons, and of course electronegativity talks about the fact that the oxygen should pull the electrons more in that direction, and they're going to pull the electrons in this direction. We get our dipole moments pointing away from the carbons. Now what we're going to do, and so we're going to, by ignoring electronegativities, we're going to do is split the bonds in half, and we're just going to say, you know what, both elements are going to get their electrons back. Okay, so we just split this in half and we ignore electronegativities, and we're just giving the electrons back to the atoms. Essentially what we're doing is we're trying to account for how this arrangement in the molecule changed from the original arrangement for the oxygen. Okay, oxygen started with 6 valence electrons. We want to see how that compares back to the original structure. Okay, so I'm going to go through and I'll show you how to calculate formal charges, and then I'll show you what we do to determine the correct structure. Okay, so let's go ahead and look at our example for carbon dioxide. And here's your rules. So what you're going to do is you're going to have a formal charge, and in order to calculate it, you're going to take the number of valence electrons, and this is from the periodic table. Okay, so you're going to look at the base element and how many valence electrons it originally had. And over here, in this bracket, what we're looking at is the atom in a bond. Okay, so we're looking at the atom in the compound. Okay, so in here we're going to compare the original element to the element in a compound. So what we do is we look at the lone pairs of electrons, and they take half of the electrons. Okay, so what I'm going to do is I'm going to calculate the formal charge of oxygen. Now I have two different oxygens, so I'm going to call this oxygen A, and I'll call this oxygen B. Now they're really going to be the same because of the way they look, because they have the same electron arrangement. So I'm going to do oxygen A, and I'm going to calculate the formal charge. So if I look at my periodic table, okay, we all know that the oxygen has a valence electrons of 6, okay, and carbon has valence electrons of 4. Okay, so that's the original element before it gets put into a bond. So I'm going to start with, for oxygen, 6, and this is going to actually be oxygen B as well. So I'm not going to do the calculation twice because it's going to be the same thing. And then for carbon, I'm going to start with 4. Then I look at the electrons in the lone pairs. I have 1, 2, 3, 4. So I'm going to subtract out 4 plus 1/2 the number of bonding. Because remember I said we're going to split this in half and give the electrons back to each element. So therefore, I'm going to have 2 electrons, because each double bond has 4 electrons. So 2 electrons back to the original element, in this case oxygen. So that would be 4 plus 2 gives me 6. So 6 minus 6, of course, is 0. And I do the same thing for carbon. Now carbon has no bonding pairs of electrons, right? There's no lone pairs of electrons on the carbon, but for each of these bonds I split them in half. I get 1, 2, 3, 4. So I'm going to add 4 and I'm going to get 0. Okay, so my formal charges for the oxygen here is going to be 0. For carbon it's 0, and for the oxygen it's 0. And that's good. That's what we want to have. We want to have the electrons distributed evenly throughout the structure. Now, watch what happens over here. We got the oxygen with a triple bond and an oxygen with the single bond. So I'm going to call that A and B. And I take oxygen A and I calculate it just like I did before. So starting with 6 minus 1, 2, lone pairs of electrons. And then I split this in half. So 1, 2, 3 plus 3. So now I'm going to have 6 minus 2 plus 3, which gives me, not 5, but 1. Okay, so this has a formal charge of plus 1. Notice I write the charge in front, not like I do for actual ions where I put it in the behind, right behind it, I put it in front. Okay, so my other oxygen, oxygen B, again the same thing, 6 minus, and then I look at 2, 4, 6 plus 1 for the single bond. That gives me a value of minus 1. So over here I have a value of minus 1 for this oxygen. And the carbon is going to be 4 minus, again 0 because there's no lone pairs of electrons, 1, 2, 3, 4. So plus 4 gives me a value of 0. So the carbon is 0. Okay, so what does this mean? What do these charges that I'm putting in here mean? Well, when the atom oxygen goes from its elemental state, or the way that we find it on the periodic table, it has 6 valence electrons. So when it bonds, these electrons here bond with the carbons. And that's what makes sense of, it seems to work when we write carbon dioxide in this fashion. Over here, why would this oxygen, this one over here with the single bond, why would it have 1, 2, 3, 4, 5, 6, 7? Why would it have 3 sets of lone pairs of electrons? In the original state, it only has 2. So why would it do that? Why would this one lose its electrons? See, it doesn't make any sense for it to have done that. So what that means is that this oxygen, going from its original state, somehow, some way when it forms this bond, has gained an extra electron, whereas this one has lost it. And that doesn't make any sense. There's no way you can really explain that, because both oxygen, so they both should have the same electronegativity. There's no reason why electrons would move this direction in the molecule. Okay, so point is, what you're looking for is the numbers to be as close to 0. You want them to be 0, like over here. This is good. So you want the formal charges to be 0 or as close to 0 as possible. So if you can get one that's all zeros, that's going to outweigh one that has positives and negatives in it. Okay? So now if it does have a charge, like let's take a look at one that has a charge in it. Let's take a look at sulfate. Okay, since it's a sulfate ion, there's a 2- charge on here. Okay, now when I look at that 2- charge, what that means is that 2 extra electrons have gone into the structure. Okay, so in this SO4, 2 extra electrons have been put in to make it overall -2. So where did they come from? Well, let's go ahead and calculate formal charges. Okay, all of these oxygens are going to be the same, so I'm not going to separate them out. I'm just going to calculate sulfur and oxygen. So sulfur, if we look at the periodic table, it's going to have 6 valence electrons, just like the oxygen does. So they both start off with the same number of valence electrons. Okay, so 6 valence electrons here, minus, and again we look at the number of lone pairs of electrons around sulfur. There are 0, plus 1/2 from each of the bonds. So therefore I have 4. So what if I look at calculating this? It's going to be +2. Okay, oxygen is going to have 6 in the beginning, minus 2, 4, 6, and we're going to have plus 1, because you're going to break each of these bonds in half. Okay, so therefore we calculate this, we end up with a minus 1. So we get minus 1, minus 1, minus 1, minus 1, and for the middle, we get plus 2 for that sulfur. So if I add up all these formal charges, minus 1, minus 1, minus 1, that's minus 4, and plus 2 gives me a net result of 2 minus, which matches the overall charge of the ion, which is good. Now, what this is saying is that the electrons, they're pulling more electrons from the sulfur, because if you think about sulfur, it started with 6 valence electrons. But in this bond, somehow it now only has, it's lost some of those, its lone pairs of electrons have been lost. So this is not looking too promising. So let's calculate and look at this structure here. And by the way, I should have had brackets around these. I just left them off so I could write in there. So this should technically have a bracket with a 2 minus charge for a correct Lewis structure. Okay, so sulfur, 6 minus, let's see, there's no lone pair, so that's still 0. Cut this in half, and this one, so 1, 2, 3, 4, 5, 6. So plus 6, charge here is 0. That's looking pretty good already, because if we want the numbers to be close to 0 as possible, each oxygen starts out as 6. Now I've got two types of oxygens. I got A and let's call this one B up here. Okay, these two are the same and these two are the same. So let's calculate oxygen A. So that would be 6. Okay, so we have 6 for the oxygens, and let's see, 1, 2, 3, so 4 plus 1, 2. So here we get 6 minus 6 gives me 0, which is again very good. And B, we look at 6 minus 2, 4, 6 plus 1. So that would be 7. 6 minus 7 is going to give me minus 1. So just a minus 1 here, a minus 1 here, a 0, and for the middle, a 0. So this is definitely a better shape or better structure for the sulfate. Now, if you go back and try to explain that, looking at the structure, why is it that this oxygen and this oxygen get that lone, why is it that they're getting that extra electron? And that's what we're seeing here. We're seeing where are those two electrons at. Well, it looks like they're going to be on those oxygens here and here. Okay, but remember, this isn't really the right structure, because if we have the lone pairs, so if we got a double bond and a single bond in here, you should draw this as a resonance structure, right? So that means that those electrons aren't really there and there, they're also here and here at the same time. That's where the whole quantum mechanic thing gets kind of confusing with the electrons moving around. Alright, let's see, I think that's pretty much all I'm going to say about the formal charges. But you don't have to go through, and I've been doing some explanations here and trying to get you to understand what's going on. The AP test is never going to ask you to explain these. They're never going to say, well, why is this one better than the other one? All they're going to ask you to do is calculate formal charges, and they're going to do just like I did here, where they're going to give you two structures, and they're going to say, well, which one is more correct? And what you'll do is calculate formal charge, and you'll choose the one that's closest to 0, and that's pretty much the end of it. Okay, so the explanation hopefully kind of gives you a little bit more insight into what's going on. And that's pretty much it. So thanks a lot.